This video looks at scatter plots, line of best fit, and regression. Now, line of best fit and regression are 10A topics, but interestingly, all of this leads into both general maths and mathematical methods. So very, very important for both subjects. And we are going to focus on the technology rather than doing it by hand, which again you will need in both general and maths methods. Now, data which involves two variables is called bivariate data. Bi meaning two, so two variables. When interpreting relationships that involve bivariate data, big word of warning, do not assume that a strong connection or correlation means that one was caused by the other. Okay, so in psychology, this is looking at cause and effect. Just because one thing has a strong relationship to the other doesn't mean it causes it. So if I have a really long arm, yes, I may also be tall, but my long arm doesn't cause me to be tall. Okay, so just be careful when you're making interpretations or conclusions that you don't assume that one causes the other. Now let's look at scatter plots. A scatter plot can be used to display bivariate data and show if any connections that might exist. So it gives us a visual of what's happening between the variables. Now scatter plots show whether the trend is linear or non-linear. And if the trend is linear, we're going to decide whether the strength of relationship between the variables is strong, moderate, or weak. If you go into mathematical methods, you'll look at things other than linear. Okay, so you might look at exponential, for example. So when we're looking at these scatter plots at the bottom, the first one is a perfect negative relationship or correlation. So the correlation is a -1. Correlations have to lie between 1 and -1. So R is going to be between +1 and -1. Meaning that if our correlation is either -1 or 1, it is perfect. It is a perfect correlation. So if you look at this scatter plot, I could draw a straight line going through every data point. That is why it's perfect. The straight line will fit every single data point. So my correlation is -1. Negative showing the direction, 1 showing the strength. If we look at the next one, I could fit a line through the middle of these data points. Okay, so we're saying there's a negative relationship. It's pointing in the negative direction, slopes down from left to right, and our correlation might be around -0.7. So a moderate correlation there, and it's linear. The next one, no relationship or correlation. Our R equals 0. So when R equals 0, we have no correlation. I couldn't fit a graph to this data. Now let's move into our positive relationships. First one, I could fit a straight line through the middle of my data. I could probably do a better job of that, but anyway, that's a positive relationship sloping up from left to right, and our correlation might be around the 0.7, so a moderate positive correlation. Then in the last one, we have a perfect positive correlation. A straight line would go through every single data value. So our R is 1. Now, linear regression and making predictions. It's important to understand what you can do. Now, scatter plots of bivariate data can be used to make predictions based on the data collected. That's why we do it. We want to try and find a relationship between our variables so we can find an equation between the two, so then we can predict different values. So we might find data between two different points. We might do an experiment and say, this is our temperature between these time values. Well, what would we expect our temperature to be when the time was this? Or if the temperature is this, what time would that occur? They're the kind of things we're trying to do, making prediction. So where the relationship between the two numerical variables appears to be linear, it's useful to draw a line of best fit, as you just saw with those correlation graphs. Then we can find the equation of the line, and then we can use the equation to predict new data points. Now, if we are predicting new data points within the data range that we collected, so for example, if I was looking at heights of people and I wanted to predict heights, I might have looked at school 12 to 17-year-olds. So if I collected the heights for 12 to 17-year-olds, and I've said, okay, well, looking at this, I've got a 13-year-old. How tall do I think they'll be? That would be a prediction within our data points because I collected either side of that. So the reliability of those predictions depends on the strength of the relationship between the variables. So the higher my R value is, the better the prediction will be. Okay, so higher R is, or closer to -1 or 1, better prediction. Okay, if our R is quite low, then our prediction's not going to be very accurate. So it depends on the strength of the relationship. Now, extrapolation means we're predicting outside our data range. So if I wanted to use the data that I collected and I said, okay, well, I want to predict how tall a 6-year-old is, I've got this equation from the data I collected, and I'm going to plug in the age of my 6 and see how tall they will be. That's an extrapolation because it's outside of my data range. Okay, so the accuracy of extrapolation depends on whether the model is valid outside the data points. Okay, so if I said that height was linear and we grew so much for each year, then that would work for a 6-year-old. It would be, it would be quite accurate. But you would then go, well, what if I wanted to use that model to predict the height of a 90-year-old or a 40-year-old? We all know that we stop growing at a certain height. At a certain age. We also know that we start shrinking at a certain age. So our prediction is not going to be as accurate. Okay. Another one is if we were looking at population of kangaroos, that might keep increasing up to a point where there isn't enough food available anymore, and then it starts to plateau. Okay, so be careful when you're predicting on whether it's an interpolation or an extrapolation. Now you can hand draw a line of best fit, but it isn't very accurate. Also, when the data isn't linear, a line of best fit is not appropriate. So we are going to use technology to draw our lines of best fit, and that mathematically minimizes the squares or the vertical distances between each point and the line. Okay, so when we're looking at a scatter plot, if we put a line through the middle here, what our computer is going to do is look at how far these points are from our line of best fit. Okay, so the values are squared, so positive distances to the points above and the line don't cancel each other out. And that's called a least squares regression line, and we'll be talking about that. Don't get too caught up in the process of this. That'll be something that you'll worry about later on, especially if you go into general maths. We're just going to look at, I just need you to understand what it means, okay? So the equation of this line would be the least squares regression line. So what we're trying to do is minimize the distance of our data points from our line of best fit. Now, technology can also be used to determine the equation of the regression line and also the coefficient of determination. And our coefficient of determination is our R squared. Now it's r squared because we don't care about whether it's positive or negative, whether it's sloping in the negative or positive direction. All we care about is the strength. Okay, and again, our r squared, the highest it can be is 1, but because we're squaring, the lowest it can be is 0. So 0 will be no relationship, and 1 will be a perfect relationship. So the closer our r squared is to 1, the stronger the relationship, the better our predictions will be using that. Okay, this will make a bit more sense when we get to an example. So here's an example. Consider the following table of data that shows the marks for 10 students taking science and mathematics tests. So we've got a student, we've got their science mark out of 30, we've got their maths mark out of 40. We're going to use Excel to draw the scatter plot for this data and then find the equation of the least squares regression line, or the line of best fit. We're going to use the coefficient of determination to comment on the strength of the relationship between the two marks. And then we're going to make predictions. So if Trev scored 22 for science, predict his maths mark. If Sonia scored 29 for maths, predict her science mark. And we're going to comment on the accuracy of these two predictions. Don't really need the B there. So let's go to Excel and work this stuff out. Now you can see my data sitting here, and I want to create a scatter plot. So I highlight those two rows and I go Insert, and you should see Charts. You want a scatter plot. So choose a scatter plot without the line. So there's my scatter plot. I'm just going to move that across so you can see that better. Put in a new title. So students marks for science and maths. If you come up to add chart element, you can pick horizontal. This is the science mark. And that was out of 30. Then add our vertical axis. And that was our maths mark out of 40. So we've labeled everything. Now, if you click on the graph, you can see these options here. If I press plus, I want to choose the trend line. So I'm going to click trend line, and you can see that line of best fit is now on the graph. Okay, there's also a little arrow next to trend line, and I want to go to more options for that, but it already opened before because I was playing around anyway. So if I click on the graph toolbar, it says linear. So if I chose exponential, for example, it'll change that graph, but I want linear. These other options are what you might need for maths methods next year. I'm going to display my equation on my chart, and I'm also going to display my r squared value. I'm going to move those so you can see them better. So you now have the equation of this line of best fit being y equals 0.6267x plus 19.132, and your r squared of 0.8134, which is quite high, so indicating a strong relationship. Okay, so that's how you can create a scatter plot and put in a trend line in Excel. So you'll see that I've just copied that graph into my slide so I can talk about it. So there is my line of best fit. You can see the data points. We've got our equation here, and then we've got our r squared here. So it says if Trev scored 22 for science, predict his maths mark. Now science is on our x-axis. So science is x. So we've got y equals 0.6267x plus 19.132, and we have x is 22. So that's going to be equal to 0.6267 times by 22 plus 19.132. And then go to your calculator to work that out. So 0.6267 times 22 plus 19.132, and that is approximately 32.92. So therefore, predict a maths mark of 33, because you'd round up. Can't get 32.92. If Sonia scored 29 for maths, predict her science mark. So again, the formula 0.6267x plus 19.132. So now we're being given her maths mark. So y equals 29. So we've got 29 equals 0.6267x plus 19.132, and we're solving. So we're going to take away the 19.132 from both sides. 29 minus 19.132 is 9.868 equals 0.6267x, and then divide both sides. So we have x is 9.868 divided by 0.6267 is approximately 15.75. Therefore, predict a science mark of 16 for Sonia. I might write for Trev up here. Now, comment on the accuracy of these two predictions. Now, when we're looking at Trev was a science mark of 22, and you can see that our science marks in our original data went from 10 to 27. So for part C, that's an interpolation. Okay, so it's interpolation. Our R squared is 0.8134, which is quite high. So you might say a strong relationship. Therefore, prediction is relatively accurate. Okay, then for part D, Sonia scored 29 for maths. If you look at our maths marks, they went from 25 up to around 36. I could look at the raw data to get that. But her mark of 29 is between that. So it's still an interpolation. R squared is 0.8134, and it'd be the same deal, which indicates a strong relationship. Therefore, prediction is relatively accurate. Okay, if I wanted to predict Sonia's science mark if she scored 15 for maths, so just say she was down here, That would be extrapolation, and that would therefore depend on the relationship continuing beyond the data. Okay. So practice exercise 9H, page 609, questions 3, 4, 6, and 7, and use technology for those that you can.